right. So you can see my wheels here. The video did a good job explaining it, but I wanted to illustrate it with my wheels. You can see my wheels, right? Yeah, they can see my wheels. All right, so this wheel is going to stay going the same speed as I roll it at. This wheel is going to be slowed down by these tubes here. So here we go. No, I messed up. Boom! You can see it turned. This wheel slowed down, this wheel kept going, and so it turned. If somehow this had been like some kind of conveyor belt that had sped up this wheel, then it would have gone zoom. This wheel would have sped up, and this wheel would have stayed the same speed, and so it would have traveled a farther distance than that wheel and gone that way. Yeah, you can see that. So now I want to give you a demonstration by feeding my invisible fish. That's why I couldn't sit here or here for safety. The fish consume, because they're invisible, they consume electromagnetic radiation at a wavelength of 532 nanometers. Very special formulated fish food. Will you turn off the light, please? There. Okay. And I'm going to turn off this light. And this light. And this light. All right, very good. Okay, so we've said before that we've used the speed of light in our calculation 3 times 10 to the 8 meters per second. That is the maximum that light can go, and it's kind of cool because even if you're in a spaceship going half the speed of light, the light that you would see coming out would go 3 times 10 to the 8 meters per second, but the light that someone would watch coming out of your spacecraft, they would see you going at half the speed of light, and then they'd see the light coming out at just the speed of light, not the speed of light plus half the speed of light, which is what makes light really weird and why time dilation and all that is possible. But maybe we'll get to talk about that more later. Anyway, denser materials can slow down light, like they were saying, those keys. My shirt went. So my laser light is going fast in air, close to that 3 times 10 to the 8, and then in water it is slowing down. It is not changing direction right now because I'm pointing straight in. Both sides of the laser beam are hitting the water at the same time. We got the left side and the right side, or whichever y'all see. I don't know. But watch, I'm going to tilt it this way. I hope the camera can still see everything. I just got the screen off, so I can't see. All right. Oh. There we go. So, as you can see, I'm almost pointing it straight. Isn't that cool? You can kind of see the beam. I wonder if the camera can see it. Hopefully the camera can see the beam here. Best I can do. So you can see this thing is going way down into the water. I'm pointing it almost straight. It should be going straight. So what's happening is the bottom side of the beam that side hits the water first, it slows down. The top side of the beam is still going fast. So that's why the beam turns, just like my little wheels did. So it's kind of cool. And you can see there's a bunch of little dots. There's a dot. There was a dot on my hand. I'm seeing if I can move my hand. So there's a dot on that board, which I think is reflecting. This goes down here and hits this side, and this side reflects it back to over there. And it refracts when it comes out of the water. And it bends the other way because it speeds up that way. This one's slowing down. So the one that hits first, it turns that way. This one, the one that hits first, the top side of the beam hits first, and it speeds up, so it turns the other way. Kind of neat. So we can do math with this. Your assignment today asks you, will you turn it back on just that one near you? Oh, that's fine. Yeah. We can do math assignment asked you some conceptual type questions, and some, are you still recording? Good. And some math questions, I think. Where is it? Oh. Oh, the projector's going to take forever to turn back on now. So with our calculations, we're going to be doing the index of refraction. Can't see what I'm doing at all here. Hopefully they can see some stuff. The index of refraction says how much that material slows down light. So if the speed of light in the vacuum is 3 times 10 to the 8, and something has an index of refraction of 2, that means the light goes twice as slow in it. So if light's normally 3 times 10 to the 8, then light in that material would go 1.5 times 10 to the 8. Or if an index of refraction of something is 3, then instead of 3 times 10 to the 8, it might be 1 times 10 to the 8. It would be a third of it. Because they go 3 times as slow. Alright, let me make sure I have that pointed right. Well, I mean, that's kind of well, I can probably do that. What's that commercial here? Okay. Okay, all right, here we go. Air is not a vacuum. A vacuum is like in space where there's no atoms anywhere. Light can travel through that, unlike sound waves, mechanical waves that we've been talking about. Light does not need a medium to travel through. Electromagnetic waves is what light is. Don't need a medium. They can travel through nothing. But air has stuff in it. It has molecules and stuff. You know, we breathe it and stuff, so we know it's there. There's wind. But light goes almost as fast through air as a vacuum. Oh man, the rocket launcher's coming on. I'm going to there. Okay. So in air, we're going to use 3 times 10 to the 8 also. It's technically a little bit less, but we'll just use 3 times 10 to the 8. It's fine. Right, so I'll do number 1 for you. It asks, what is the speed of light passing through a medium with an index of refraction of 4.5? So another way to think of the index of refraction is a ratio. It's the ratio between the speed of light in a vacuum to the speed of light in the medium. And this ratio is 4.5. But just like I said earlier, you can also think of that like this material makes light go 4.5 times slower. So you just take the speed of light, divide it by 4.5, and you get the new speed of light through that material. So it asks what's the speed of light passing through a medium. You've got to be careful because, I mean, you can't just say, and as for the speed of light, it's 3 times 10 to the 8, idiot. You can't do that because there's 2 speeds of light. C is the speed of light in a vacuum. V is the speed of light in the medium. So this is asking, what's the speed of light passing through a medium? So this is asking for V. That's a V. Index of refraction of 4.5. That's N, index of refraction. And the speed of light, C, is 3 times 10 to the 8 meters per second. All right. So our formula is N equals C over V. That's that ratio thing. N is the ratio of C to V. And let's figure it out. 4.5 equals 3 times 10 to the 8 divided by V. First, we want to get V out of the denominator. It's really difficult if you, I mean, it's not really, but it's more difficult than we want for it to be underneath there. You've got to take a reciprocal of both sides at the end, and that's hard. So don't do that. We just want to multiply and divide. So it says divided by V. I'm getting it out of there by multiplying by V. One on top, one on bottom. just says 3 times 10 to the 8 on that side now. And that's meters per second. And now it says 4.5 times V over here. Now this is easy. Now we can say it says 4.5 times V. I just wanted to say V equals, so I'll divide both sides by 4.5. And what you should get is, instead of times 10 to the 8, it's now times 10 to the 7. So you can tell that it's 4.5 times less than 4. And we're not answering this question. This is for number 1. Anyway.